Welcome back to JVM Internals Crashcasts. I'm your host Sheila, and today we're diving deeper into the fascinating world of GT compilation. We're in the second season, JVM Adept, exploring operational understanding of the JVM. In our previous episode, we discussed tiered compilation. Now we're moving on to a crucial aspect of GIT compilation, optimizations. Victor, are you ready to unravel this complex topic for our listeners?
Absolutely, Sheila. I'm excited to explore the various optimizations that make the JVM such a powerful runtime environment. These optimizations are key to understanding why Java applications can perform so well despite being compiled at runtime.
Before we dive in, I'd like to pose a quiz question to our listeners. Here it is. In a typical Java application, what percentage of performance improvement can be attributed to JIT optimizations? Is it A, 5 to 10%, B, 20 to 30%, C, 40, 50%, or D, 60, 70%? Think about it, and we'll reveal the answer at the end of the episode.
That's an intriguing question, Sheila. It really makes you think about the impact of these optimizations. I'm sure our listeners will be surprised by the answer. While we don't want to give it away just yet, I can say that the impact of JIT optimizations is often underestimated.
Agreed, Victor. Now, let's start with the basics. Can you explain what we mean by optimizations in the context of JIT compilation?
Certainly. In GT compilation, optimizations are techniques used to improve the performance of the compiled code. The GT compiler analyzes the bytecode as it's being executed and applies various transformations to make it run faster. These optimizations can range from simple tweaks to complex transformations of the code structure.
I see. So it's like the JIT compiler is constantly looking for ways to make our code more efficient. Can you give us an example of a simple optimization?
A great example of a simple optimization is constant folding. This is where the compiler calculates the result of constant expressions ahead of time, rather than during program execution. For instance, if you have a simple calculation like multiplying 5 by 60, the JIT compiler would replace it with the result, 300, saving a multiplication operation when the program runs.
That makes sense. It's like doing the math homework before class starts, so you don't have to do it during the test. Now, let's move on to a more complex optimization. I've heard about something called inlining. What's that all about?
Inlining is one of the most powerful optimizations performed by the JIT compiler. It involves replacing a method call with the actual body of the called method. This eliminates the overhead of the method call itself and often opens up opportunities for further optimizations.
That sounds interesting, but I'm not sure I fully understand. Could you provide an analogy to help our listeners grasp this concept?
Of course, think of inlining like a recipe in a cookbook. Normally, when you're following a recipe and it says, add the sauce, you might flip to another page to find the sauce recipe. Inlining is like copying the sauce recipe directly into the main recipe, so you don't have to flip back and forth. It saves time and makes the whole process more efficient.
That's a great analogy. I can see how that would speed things up. Are there any drawbacks to inlining?
Good question, Sheila. While inlining can significantly improve performance, it does have some drawbacks. The main one is increased code size. If we inline too many methods, we might end up with much larger compiled code, which can put pressure on the instruction cache. The GT compiler needs to balance the benefits of inlining with the potential drawbacks.
Interesting. Now let's move on to another optimization you mentioned earlier, loop unrolling. Can you explain what that is and how it works?
Certainly. Loop unrolling is a technique where the compiler takes a loop and repeats its body multiple times, reducing the number of iterations. This can improve performance by reducing the overhead of loop control and potentially allowing for better instruction pipelining.
That sounds complex. Can you break it down with an example?
Sure. Imagine you have a simple loop that adds numbers from 1 to 100. Instead of repeating the process 100 times, loop unrolling might transform it to do this 25 times, but adding 4 numbers each time. This reduces the number of checks and increments, potentially speeding up the loop.
I see. It's like bundling tasks together to reduce overhead. Are there any situations where loop unrolling might not be beneficial?
Absolutely. Loop unrolling increases code size, which can be a problem if it leads to increased instruction cache misses. Also, for very small loops or loops with a low number of iterations, the overhead of unrolling might outweigh the benefits. The JIT compiler uses heuristics to decide when loop unrolling is likely to be beneficial.
That makes sense. It seems like there's a lot of decision-making involved in these optimizations. Are there any other important optimizations our listeners should know about?
One more crucial optimization is escape analysis. This is where the JIT compiler determines whether objects created within a method escape that method, meaning they're passed to other methods or returned. If an object doesn't escape, the JIT can often allocate it on the stack instead of the heap, or even eliminate the allocation entirely. This can significantly reduce the pressure on the garbage collector.
Wow, that sounds powerful. It's like the JIT compiler is constantly looking for ways to make our code more efficient, sometimes in ways we might not even think of as developers. How do these optimizations impact real-world applications?
The impact can be substantial. In many cases, well-optimized Java code can perform comparably to, or even better than, natively compiled languages like C++. These optimizations allow Java to combine the benefits of a high-level, portable language with performance that rivals lower-level languages.
That's impressive. Before we wrap up, let's reveal the answer to our quiz question. Victor, would you like to do the honors?
Certainly. The correct answer is C, 40 to 50%. JIT optimizations can often provide performance improvements in this range, which is quite significant. Of course, the exact improvement can vary depending on the specific application and how it's written.
Thank you, Victor. To summarize today's episode. 1. JIT optimizations are techniques used to improve the performance of compiled Java code. 2. We covered several key optimizations: constant folding, inlining, loop unrolling, and escape analysis. 3. Each optimization has its benefits and potential drawbacks, and the JIT compiler must balance these carefully. 4. These optimizations can lead to significant performance improvements, often in the range of 40–50%. In our next episode, we'll be moving on to the class loading in depth chapter, starting with the class loader hierarchy. Don't miss it. If you've enjoyed this episode, please subscribe to JVM Internals Crashcasts and leave us a rating. Your support helps us continue to demystify the complex world of JVM internals. Until next time, keep optimizing.